Welcome to Analog Electronic Circuits. Today is the 13th lecture and we are going to continue from where we left off in the last class, and then we are going to start with an introduction to current sources in this lecture. Okay. So, in the last class we had hypothesized, or rather we had suggested that maybe an amplifier that looks like this will do a reasonably good job. This was the cascode amplifier, all right, and the cascode amplifier has the first stage as common source, the next stage as common gate. The gate is grounded. So, it is common gate, the first stage is common source. So, the input is applied at the gate of the common source amplifier, right, and then on one hand it sees RDS of the bottom transistor, on the other hand it sees the impedance looking into the source of the top transistor, which happens to be low. So, the GM current chooses to go through the source and not through RDS, right. So, therefore, the transconductance, the short circuit transconductance of this structure is almost equal to GM. At the same time, the output impedance looking in from the output node is very high, because this is a MOSFET terminated on the source side with RDS. So, on the source side there is RDS, and on the you are looking in from the drain. So, the effective impedance looking in from the top is RDS 2 times GM 2 times RDS 1 plus RDS 2 plus RDS 1. Okay, it is GM 2 plus GMB 2, right. So, change that. All right. So, this is the effective output impedance, and this happens to be a large quantity. The output impedance times the same old transconductance GM gives you a reasonably large intrinsic gain. But to get this intrinsic gain as close to the actual gain as possible, or rather to get the actual gain as close to the intrinsic gain, what do we need to do? We need to make sure that the load is also a similar very large impedance. Okay. Just having a self output impedance is not good enough, the load also has to have a very high output impedance. So, here we make a PMOS structure, and this is nothing but the load. Okay. Once again, common gate, and the top one is nothing but just an RDS. The top one is not even a MOSFET. I mean, effectively all it is doing is it is providing the required RDS. No, it is actually a better idea to have a MOSFET over there, not a resistor, right. So, do not place a resistor. Yeah, MOSFET is what it is. Okay. So, this is the structure that we had, and these resistors give the required voltages at the gates of these individual devices. And where is the output? You can take the output from here. All right. So, this is the overall plan of the circuit. So, this is what we had done in the last class. This is the complete picture, including both small and large, small signal as well as DC biasing, everything is incorporated into this picture. And then we need to briefly talk about the swing limits, or in other words we need to talk about how to maintain saturation, that is how to maintain M4, M3, M2 and M1 in their respective flat regions of operation. okay, because that is required, that is absolutely required. All right, so we need to talk about that. And how do we, what do we do? So, the first thing is you are going to get a certain VGS for M1, and that is very important. This VGS is important because this is what is creating the GM. This VGS of M1 is what is responsible for creating the GM, VGS minus VT. All right. Then, if you have so much VGS minus VT, then this VDS has to be more than that at all times. At all times, it has to be more than that. Now, let us understand one more thing. The impedance looking into this node is low, right, because on one hand you see M1, the drain of M1, on the other side you see source of M2, and looking into the source of M2, the impedance is low. Now, if the impedance is low, then automatically that means that the amplitude of the signal at this node is not going to be very high. Do you agree with that? If you have a given current amplitude and the impedance is low, then the voltage amplitude is going to be small. You apply a signal, GM1 times the signal is the amplitude in the current through M1, signal current through M1. This signal current is seeing a certain impedance at this node, right, Thevenin equivalent impedance of the rest of the circuit, and that creates a voltage at this node, right. So, that impedance happens to be low. So, therefore, the voltage over here is also going to be low. Okay. So, this voltage is not really going to swing much, no swinging, right. It is a very low amplitude voltage, it is not really going to move much. The voltage here is going to move, not here. All right. What is this voltage going to be? This voltage is going to be the potential at the gate minus the requisite VGS. You see, the potential at the gate is fixed minus the requisite VGS, that is the approximate potential of this. There is going to be some swing, a little bit of oscillation around that, but it is not very significant, it is a small signal. All right. So, if I make sure that this VDS is sufficient to maintain M1 in saturation, then that is good enough. This voltage is not going to swing, this voltage is more or less static. Okay. So, let us think about it. Let us say you know your VT is 0.5 volts, and let us say I want to maintain a gate overdrive of 0.2 volts, in which case the voltage here has to be 0.7. Oh, you wanted to do bias stabilization. Okay, great, that is a good idea. We want to do bias stabilization. So, this is wrong. You add one more resistor over here to stabilize the DC operating point, and you know put a capacitor across it, so that it does not appear in the small signal. Okay, that is not a bad idea, that is actually fantastic. Okay. And let us say that you want a net current of 1 milliampere, and let us make this 1 K. So, you want 1 volt over here. So, 1.7 over here, is that okay? And we pick the device such that at 0.2 volts of overdrive, VT 0.5, 0.2 volts of overdrive, the current is 1 milliampere. We pick such a device. Now, notice this 1 milliampere is coming right through. So, all the devices now have 1 milliampere, all right, and therefore, their respective VGSs have to be created. right. So, for example, M4, let us say M4 has the same K, okay. You pick a PMOS with exactly the same value of K, right. We are going to discuss K today itself. But let us say you pick a PMOS with exactly the same value of K. In that case, this, and let us say the Vt is also 0.2 volts. In that case, this voltage happens to be 0.7. So, if I have 5 volts of power supply, then this is 4.3, done. Okay. What about here? This would also be something like 0.7, and what about here? This is also something like 0.7. Okay. So, this is the setup. So, I clearly understand that I need 1.7 volts here. So, I make sure that this resistive divider is such that I get 1.7, I get 4.3 over there. What should the values over here be at these two nodes? First of all, what should the value over here be? This is 1 volt. I have a gate overdrive of 0.2, which means VDS has to be more than VGS minus VT. So, VDS has to be more than 0.2. That means the source of M2 should be at a voltage more than 1.2. But that is all that we are saying. We are saying that any voltage more than 1.2 is good enough. It could be 1.2, it could be 1.3, 1.4, whatever you want. Is that okay? Is that understood? Great, because this voltage is not swinging either, it is pretty much static. So, 1.2 is actually fantastic, because that gives you the largest headroom across M2. So, 1.2 is fantastic. I would like to place this node at 1.2, which automatically means that this node should be at 1.9. Now, when I do the resistive divider and place this node at 1.9, then automatically this goes to 1.2. So, this voltage at the gate is what sets the DC operating point voltage at the source, not vice versa. Design wise we went backwards when I am thinking of designing, but when actually it is going to happen, this is what is enforcing. This potential divider will create 1.9, it does not have a choice. Now that it has 1.9 over here, it is going to enforce 1.2, so that it conducts the same current right through. Is this okay? All right, this is understood, I think. Okay, so I have got 1.9 volts here, I need 1.9. How about here? So, we will have this exactly the same story in the PMOS, right. This is a low impedance node. You now understand what it means, that is the impedance looking into this node is low. So, if I have some signal current, then the voltage over here is going to be, signal voltage over here is going to be low. Okay. If I maintain 0.2 volts across VSD, then that is good enough. That means, if this node is at 4.8, it is good enough, okay, because it is not really going to move much. Okay, if that is 4.8, then a voltage over here of 4.1 would be fantastic. All right, so you organize this resistive divider, pick something like 700 K over here, 200 K, 200 K, 700K and 2.2 mega ohms. Fine. So, this is the basic idea. All right, we are going to look at all of this in a lot more detail very soon. I am just trying to give you a flavor for what is coming. Okay. This is actually I am trying to set the pace over here. Okay. You might not have understood everything. For example, you might not have understood why this node is not swinging much. All right, it is okay. Just accept it, move on, right. You might not have understood exactly the idea behind the setting of all these voltages. Oh, finally, what is the swing? The possible swing over here? The maximum voltage it can go to is 4.6, the minimum voltage it can go to is 1.4. All right. Yeah. So, this is just to set the pace. You might not have understood everything. There are going to be a lot of questions, I hope, and but let us move on from here and start something fresh, because what is going to come is finally going to add back. All right. So, we are going to move on to something new. We are going to start discussing current sources. And mirrors. So, this is a very important topic, and this topic is one of the cornerstones of analog electronics, modern analog electronics. Okay. So, make sure you understand it very well. So, you all know voltage sources, right, and the dual of a voltage source is a current source. In a current source, the current is constant and any voltage can appear across the current source. In a voltage source, the voltage is constant and the voltage source can supply any current with that constant voltage. However, for a voltage source, things are usually not ideal, in which case a voltage source, when it tries to supply current, the voltage actually dips. So, this is modeled as a resistor. When it tries to push current, the voltage dips, right. This voltage is no longer V naught, it is V naught minus IRS, where this is the source resistance. Fine. So, this is a non-ideal voltage source. Just like a non-ideal voltage source, when you actually try to make a current source, there is no such thing as a current source, by the way, right. Voltage source can be made with a chemical reaction, right, but a current source can't be made with a chemical reaction, right. There are other ways to do current sources. For example, a photodiode could possibly behave like a current source in some modes of operation. If you use it right, a photodiode could behave like a current source. But anyway, by the way, we had discussed this earlier, it is all relative, it is all subjective, whether a voltage source is at all a voltage source or a current source is a subjective matter. Why? Because it all depends on the quality of the output impedance. Okay. In general, it is a power source, it is a source of power, whether it appears like a constant voltage or appears like a constant current, it is for you to decide. Okay. So, this is the model for a non-ideal voltage source, and a current source would like to produce a constant current no matter what the voltage across it is. So, it does not matter what voltage it has, right, it would like to produce a constant current, push a constant current. However, a current source is also going to become non-ideal, in which case when I increase the voltage across this, the current pushed out is no longer I naught. A portion of the current is used up. Okay. So, for example, if this voltage is V, then the current going out is I naught minus V by R s. This current is V by R s. Okay. So, the model is very similar. A non-ideal voltage source is a voltage source in series with a resistance. A non-ideal current source is a current source in shunt with a resistance. The model is very similar. In one case V naught minus I times R s, in the other case I naught minus V times G s. Okay. So, you convert, you go from voltage to current, all the elements change over. So, the resistance becomes a conductance. So, an ideal voltage source will have R s equal to 0, an ideal current source will have G s equal to 0 or R s tending to infinity. Fine, great. This is the basic understanding. Okay. As a source of power, how much power is the voltage source producing? If this voltage is something, right. Okay. How much is it generating and how much is it pushing in? How much is it delivering to? So, this is I and this is V naught minus I R s, right. This is also I. So, the power that it tried to generate was V naught times I and the power that it delivered was V naught times I minus I squared R s. Fine. Okay. How about in case of the current source? It tried to generate V times I naught, right, but what it pushed finally into the load is I naught minus V by R s, the whole thing times V. So, V times I naught minus V squared by R s, which is lost in the source impedance. Okay. In both cases, whatever voltage is there over here and whatever current goes into the load, right, the product of the two gives you the power delivered. So, it does not matter at the end of the day, it does not matter whether you model the source of power as a voltage source or as a current source. This is just a model. Okay. This is perception, this is convenience, right. Sometimes when the output impedance is large, you say that the source of power looks like a current source. When the output impedance is low, you say that the source of power looks like a voltage source. For example, chemical reaction is taking place, right. You say, right, zinc and acid, lead acid battery or zinc and acid battery. In such a case, you say that it happens to look like a voltage source. Okay. It is a source of power, right. It is chemical energy being converted into electrical energy. It is a source of power. It just happens to behave like a voltage source. Whereas, in a photodiode, right. You can have both situations. At times it will look like a current source, at times it will look like a voltage source. All that it matters is where are you on that curve, right. So, we are not discussing the photodiode over here, but in general I am trying to establish that a source of power, it is at the end of the day a source of power. Okay. Whether you qualify it as a voltage source or a current source is subjective. All right. Now, we want to make a current source, okay, for reasons that are not very obvious to you, but let us say I want to make sure that in this circuit, let us say that I want to make sure that in this circuit I want a fixed bias current 1 milliampere. I would, instead of having this resistor over here, I would place a current source pulling 1 milliampere down this entire circuit. Okay. So, that is probably my objective. Actually, that is one of the most important things that I will be doing using this current source. Okay. So, this 1 k resistor is going to be replaced by a current source to make sure that everywhere I get 1 milliampere. This is the plan. How do I make a current source? Now, the easiest thing is to recollect that the MOSFET, if you recollect the MOSFET characteristics, what do you recollect over here? Why did I draw this again? Because in the flat region, in the saturation region of the MOSFET, the current does not change no matter what VDS is, right. The drain current. So, I have got the drain, I have got the source, in between I have got something, right. In between I have got the MOSFET. Okay. But let us not draw this as a MOSFET right now. I have got the drain, I have got the source. I can change the drain source voltage, but the current is not changing. The current, this drain current is fixed. So, this is the job of a current source. So, this MOSFET is behaving like a current source. Okay. So, naturally the MOSFET is a current source. That is the basic premise. It happens to be controlled by the voltage VGS, right. For different values of VGS, I get different values of the current, but otherwise fundamentally it is a current source, because I can change drain to source voltage, it does not change, the current does not change. Okay. So, this is the ideal MOSFET. Of course, then you say that the device manufacturer can't make an ideal MOSFET, and invariably he is going to give me some slope to this curve, some slope to this curve, and so on. So, it is not going to be an ideal current source, the current will change slightly. All right. So, this is the general idea. Okay. So, generally speaking, if I just have a MOSFET, I have success. All I have to do is make sure that VDS is greater than VGS minus VT, and this MOSFET behaves like a current source. Okay. Now, if things were so simple, then I would not be spending this, I would not be talking about this as a chapter. Things are not as simple as this. You are not really very happy with this kind of these restrictions. So, you have got two restrictions. One restriction is the voltage, it has to have some minimum, and the second, a bigger problem, is the slope on this line, and this slope is not really, sometimes your boss might say that give me a better current source than this current source is no good. Okay. Can you design a better current source? So, these are the two problems. One is the output impedance of the current source. So, what is the slope? 1 by RDS, right, that is the slope, 1 by RDS is the slope, RDS is the output impedance of this particular current source. And so, slope, output impedance, is one problem. A second problem is the range of voltages, and the third problem is the value. Okay, it is a current source, but what is its value? Do you have any control over the value of this current source? Okay, so, these are my three fundamental things that I have to work on. So, the first thing that I am going to work on is the value, all right, and we change the problem of the value into a problem that is like this, that suppose I show you a current source, suppose I show you a current source of value 1 milliampere, or suppose I give you a current of 1 milliampere. Can you make another current source of value 1 milliampere? Okay. If I tell you what 1 milliampere is, can you make a current source, another current source of 1 milliampere, or can you make 2 milliamperes even? If you can make 1 milliampere, maybe you can make yet another 1 milliampere. Can you combine them and make 2 milliamperes? Can you give me 10 milliamperes? If I tell you the value of 1 milliampere, can you give me anything else? And this is called a current mirror. Okay. So, the basic circuit for the current mirror looks like this. Okay. So, somebody has given me this 1 milliampere and I have to create another 1 milliampere. So, the MOSFET itself is the current source. So, this is the source, and I have to decide what is the right gate voltage. Remember, this current source is a controlled current source, it is a voltage controlled current source controlled by the voltage at the gate. Okay. So, I have to decide what is the right value of voltage at the gate such that I get 1 milliampere. Now, what I am going to do is I am going to take yet another MOSFET, which is an identical copy of this MOSFET. So, these two are identical to each other. What does identical mean? Identical means that they have the same value of K, they have the same value of Vt and everything else. They are at the same temperature, they are co-located and so on. they are in the same region, they are in the same area, they are subject to the same environmental conditions. Okay. So, that is what identical means. So, these two MOSFETs are otherwise identical. Then I push 1 milliampere through this MOSFET, through M1, I push 1 milliampere. This was the reference current. Okay. The reference current was given to me. I used the reference current, pushed 1 milliampere, pushed the reference current through M1. Now, when I push the reference current through M1, it creates a certain VGS, it requires a certain VGS. All right. This VGS happens to be just right to place M1 in saturation. VDS of M1 is equal to VGS of M1. VDS is equal to VGS, and this automatically means that this device M1 right, this automatically means VDS is greater than VGS minus VT. The answer is yes, because VT is some positive voltage, and if VDS is equal to VGS, then you are done. All right. So, this MOSFET M1 happens to be in its flat region. So, this gate voltage that I have created over here is just right such that M1 remains in saturation and 1 milliampere comes through. So, if I apply the same gate voltage to M2, then hopefully the current here will also be equal to 1 milliampere. If the drain voltage is greater than VGS minus VT. All right. So, this is the basic premise of the current mirror. Let's go over it once again. You remember this characteristics? ID as a function of VGS. This characteristics is valid when VGS is such that VDS is greater than VGS minus VT. VDS has to be greater than VGS minus VT. Then this curve is valid. Okay. Some k times VGS minus VT the whole squared. Fine. That is this curve, parabola. Okay. Now, this curve is valid in saturation. I push 1 milliampere through the device and I make sure that VGS is equal to VDS, which means the device is in saturation, right. The device is guaranteed to be in saturation whatever value it is, because VDS is always equal to VGS for M1, guaranteed to be in saturation. Then I push 1 milliampere through it. So, I look up 1 milliampere. And this happens to be the required VGS. So, that VGS is created across the device, or rather across the gate source. All right. And then the same VGS is applied to M2. And as far as M2 is concerned, you look at the other curve, M2 also has the same set of curves, right, the same set of curves. It will, so for this VGS it will have 1 milliampere of current if the device is in saturation, or rather if the device is in saturation, then it is going to pick this particular curve, which happens to be a 1 milliampere curve, right. And if the device is in saturation, then this does not change, right. The current does not change when I change VDS. So, this is the basic premise. In one case, you are using this curve to create the operating point. In the other case, you are using the flat region of the curve to show that this is actually a current source. All right. Now, of course, there is going to be some restriction on what this load can be, right. For this 1 milliampere of current, the voltage over here should not drop to below VGS minus VT. Okay. So, the load has to be such that, right, it can't be any arbitrary resistance, for example, right. If it is 100 mega ohms, for example, then you try to pull 1 milliampere through 100 mega ohms, you get a huge voltage drop. It will not be able to sustain that voltage drop, because this is VDD, right, and automatically this device is going to have VDS equal to 0, which means that you are going to end up at this point not in saturation at all, right. So, that is not going to help. The load can't be arbitrarily large, right. There is some maximum to what the load can be, okay. And that maximum is dictated by this condition. Fine. So, this is the basic premise of the current mirror. This is your first current mirror, right. It is just a 2 MOSFET circuit. In one you push the reference current, in the other you mirror it, you create another one. All right, is this understood? Okay. Now, we are going to slightly extend things, right. If I had 1 milliampere, can I create 2 milliamperes instead of 1? And the answer is yes. So, this is your reference current. You push it through one device and you generate just the right voltage, such that if I have another MOSFET, it will create the same current, okay. And guess what? You can have yet another MOSFET and get the same current. So, this is 1 milliampere and this is also 1 milliampere, because all these devices are identical, okay. Then you combine them and now this is 2 milliampere. Any questions? So, if I have a 1 milliampere reference, therefore, I can create 1 milliampere, 2 milliampere, 3 milliampere and so on and so forth. Okay. So, the way we do this, we do not really actually at the end of the day you could implement it in this fashion, but we have some shortcuts. So, the MOS device equation that you studied, so what we projected over here was I d equal to k times VGS minus VT the whole square, okay, where k is some constant. Now, what I am going to do is I am going to expand this constant. This constant k is nothing but mu Cox by 2 times W over L, all right. Mu happens to be the mobility of either electrons or holes, whatever is the majority charge carrier. Cox is the oxide capacitance of the gate, all right. Cox is the area of the gate times epsilon of the gate insulator divided by the thickness of the gate, right, A epsilon by D, that is Cox. And W and L, what are these? W and L are the width and the length of the MOSFET gate. So, if I have a gate, so this is the gate source drain, right. I have drawn a 3D kind of a projection image body, all right. This dimension is the width of the gate and this dimension is the length of the gate, right. The length of the gate is the length of the channel that is formed between, that is induced between the source and the drain when the gate voltage is above V t. Okay. So, L is the length of the channel, width is the width of the gate, right. So, you can think of it as something like a resistor, right. This channel is like a somewhat like a resistor, in which case if I increase L, the current is going to decrease, right. If I increase L, the current is going to decrease, and likewise you can think of this width as the width of the channel, right, of the channel resistance, in which case if I increase W, the current is going to proportionally increase. All right. If you place two such devices in parallel, then effectively like this, right, two devices in parallel, then effectively you have got double the width. You can place another one over here, right next to it, right. You have got double the width. In such a case, right, the width doubles, so the current doubles, right, or you could draw it as two separate MOSFETs. All right. So, the current is proportional to W by L, where W is the width of the channel, L is the length of the channel, okay, width and length of the gate of the MOSFET. Fine. So, effectively what you could do is you could make so if this is I 0 and this has W 1 and L 1, and if the second device has W 2 and L 2, then this current is going to be proportional to W 2 by W 1. All right, that is how it is going to work out. You are going to get a VGS. So, here you have got W 1 L 1, that is going to create a VGS, and then you apply that VGS. Here now you have W 2 L 2, you get a certain I. Okay. So, I naught times W 2 by L 2 divided by W 1 by L 1, that is going to be your final current. And now you choose your W 2, W 1 according to however you want, what ratio of current you want between the reference and the final result, and you get the desired current. All right, is this fine? Is this okay so far? Great. So, next what we are going to do is, so we have kind of solved this problem, right. In what sense? In the sense that if you give me a reference current, I can produce another current of equal value or a value proportional to the reference current. Okay. So, if you give me a 1 milliampere current, then I can create any other current source, right, depending on W width and length, I can create any other current source. Okay. So, this value problem is done. Next what we are going to do is, we are going to look at output impedance. So, let us first think of the output impedance of the basic current mirror. So, I am going to look in from outside, what is the impedance that I am going to see, small signal impedance that I am going to see. When you are going to do small signal analysis, what will you do with this reference current source? You are going to null the current source, right. You are going to make it static, this is static. So, there is no incremental current going through this reference current source, which means that this current source is going to be treated as a current source of value 0, which automatically means that it is an open circuit. Unlike the voltage source case, a current source becomes an open circuit, right. A voltage source becomes a short circuit because its value is 0. So, here the value is 0, it becomes an open circuit. Okay. And then what are you going to do? What is this current? Gate current is 0, perfectly 0, which means the current going into this drain is 0, right. Gm times Vgs is 0, right. All of this is 0. Okay. So, effectively this entire node is like a ground, 0 volts. You do not understand. Okay. Think of the small signal model of this. GMB is not required because both body and source are at ground. Gate and drain are connected together, which means VGS is equal to VDS. Okay. So, if I apply a voltage V over here, what is going to be the current? I apply V, V times GDS is the current through this path, and the current through this path is going to be V times GM. So, the net current is going to be V times GM plus GDS. Okay. Now, I am telling you that this net current is 0 because there is a gate over here and no current can come through a gate. So, what does it mean? What does V have to be then? This current is, if this is V, then the current is V times GM plus GDS. All right. Now, I am saying that the current is 0. So, what is V? V has therefore got to be equal to 0. Fine. Okay. So, what is the impedance looking in from outside? The gate is at 0 volts, the source is at 0 volts, the body is at 0 volts. So, Gm times Vgs is nothing, gate and source are 0, body source are also at 0. So, Gmb is also Gmb times Vbs is also nothing. All you have is RDS between drain and source, and therefore, the output impedance looking in is just RDS, nothing else. Is this okay? So, this is the output impedance of the structure. Okay. Let us stop here, and we are going to carry on in the next class. We will start from here. So, today what we did was first we looked at the cascode amplifier, and then we started on with current sources and mirrors, where we discussed the properties of ideal and non-ideal current sources and voltage sources. Then we showed how a MOSFET is a nice current source right away, right in front of us, and then we made a current mirror with which we can generate any current if I know the value of the reference. Right? We recalibrated our MOSFET equation, right. K has been elucidated over here, and then now we are working on the output impedance. The output impedance of the current mirror is nothing but RDS. Okay, thank you.